Hi, welcome to another work example for AC. Now, this time we look at example 4.3a from your lecture notes. Now, the question goes, a system supplied by a 50 Hertz source, that means here is the frequency of the supply is 50 Hertz, of 230 volt AC, angle of 0 degrees, with a complex power load required or usage of 1000 VA at an angle of 60 degrees. And the question wants us to calculate the current IS flowing through, the real power that is consumed by this load, the reactive power that is required to be supplied here, and of course the power factor. We are then next required to calculate the capacitance, additional capacitor, so that we can correct the power factor to 0.86 and to deduce or to determine what is the new current value. Okay. Now we can start by looking at the apparent power formula. My apparent power formula is given as S equals to voltage times the current. Now if you look at it that way, that means the current IS is the apparent power divided by the incoming supply voltage, which is okay. So that's 1000 angle 60 degrees VA divided by 230 angle 0 degrees volt. Okay, so that will give us 4.348 amps at the angle of 60 degrees. Okay, so that's the phasor diagram of the current source. Now at this juncture, I can have two ways to do it. Either I use the S conjugate approach, or I do the traditional approach, right? Where the true power P is given as E times I cosine of the angle difference T. So in this case, it's 230 multiplied by 4.348 cosine of phase angle 60 degrees. So that gives me 500 watts. Approximately. Okay, and the reactive power Q is EI sine of the phase angle T. That's 230 times 4.348 sine of the 60 degrees. That gives me 866 VAR. Okay, so I have this. Next, I want to calculate the power factor. So power factor FP is the cosine of the angle, which is 60 degrees. That's 0.5. Now, is it lagging or leading? The voltage is at 0, whereas the current is 60 degrees ahead. So it is a leading power factor. Alright, so that's one method of doing it. Now the other method of doing it, we can say, or if you want to do it, is to calculate is to derive it from here, the power The complex power is 100 VA at an angle of 60 degrees, right? Now this one, if I convert it to the rectangular format, I will have 500 plus J866. So this 500 is the real power, and this is the 866 is the reactive power. Okay, two methods to do that. Now that's part A. That's part A of this question. Now, part B of this questions wants us to determine the extra capacitance so that we can add on to this circuit to improve the power factor to 0.86 and to determine what's the new current value, right? Current source value. So how do we do that? The power factor correction method. The original power factor was 0.5 leading, right? 0.5 leading. Now what we want to do is we want to improve the power factor so that it becomes 0.86. Now, while doing this, the key important part is the real power remains constant, P. Real power, which we calculated as 500 watts earlier, right? 500 watts earlier remain constant, right? So the new angle theta 1 0.6, right? So this gives me theta 1 is cosine inverse of 0.86. That's 30 degrees, 30.68 degrees. And the new relationship means that this angle, the tangent of this angle, tangent theta 1, is the new reactive power divided by the real power. So the new reactive power will be Q1 is equals to P tangent of theta 1, which means 500 times tangent of the angle, which is 30.68 degrees. So the new reactive power will be 296.68 VAR. Alright, at this juncture, it's good to have an idea what's going on. So if I were to draw the power triangle, then we can see it clearly. Okay, the original power triangle was something like this. This is the original apparent power, and this is the resistive power, which was 500 watts, and the original reactive power, right, we calculated that earlier, was 866 VAR, right? And the power factor has an angle of 60 degrees. Now the new power triangle will be something like this. The power P still remains the same. Alright, the new power this power remains the same, but this time, because the angle is now smaller, so the new apparent power is just here. That means now I need to have an extra reactive power, right? The original reactive, the new reactive power here, Q1, we only need 296.68. That means I must find a way to provide this new reactive power in the form of a capacitor, right? So that I can move this down and gives me a new angle of 30.68 degrees. Alright, in other words, QC, the reactive power that must be provided by a capacitor, because this is inductor, so capacitance will force it to come down, must be the original reactive power minus the new reactive power that we need. Right? So that's 866 minus 296.68. That gives us 569.32 VAR. Okay, we need to introduce a capacitor so it will provide this reactive power to us. Now QC can be calculated from this relationship. The voltage, the square of the voltage, divided by the capacitance reactance. Okay. In other words, I need to introduce a capacitor in such a way it will provide me this reactance. So this is E square over QC. So equals to 230 square over 569.32 VA. That means the XC I need is 92.92 ohms. Now we know XC can be calculated from this formula. XC is 1 upon 2 pi F, the capacitor's value. Okay. So rearrange this formula, I will therefore the capacitor value that I need is 2 pi F XC. That's equals to 1 upon 2 pi 50 Hertz and 92.92 ohms. That gives me a capacitor value of 34.26 microfarad. Okay, so that's the capacitor I need to add to connect to the original circuit in order to improve the power factor. In other words, I need to add in a capacitor at this point. Okay. And the value of this capacitor is 34.26 microfarad. If I want to improve the power factor to 0.86. Alright, so that's for part 2. Right, okay, one last part we need to do is to calculate the new current. Right now I have this new capacitor. What's the current? Now the effect of improving power factor basically does two things to us. Number one, it reduces the apparent power required, and as a result of that, it reduces the current as well, right? So what we need to do is to calculate the new apparent power. So the new apparent power S1, the new apparent power S1 can be calculated from Pythagoras theorem. Now what happens is that the new equation becomes like that. P is 500 watts. The Q now has dropped to 296.68 VAR. Okay, now I want to know what is the new apparent power S. The angle is 30.68. So new apparent power can be the square of this and the square of this, right? So I can just say 500 square plus 296.68 square, 6 square, the whole thing square root using Pythagoras theorem. So the new apparent power now is 581.46 VA. It has dropped, right? Remember the original apparent power was 1000, right? The original apparent power was 1000 VA at an angle of 60 degrees. Okay. Now it has dropped to 581.46 VA at an angle of 30.68 degrees. So with this, I can now calculate the new current I1, and I1 is equals to the new apparent power divided by the applied voltage, right? So that is 581.46 angle of 30.68 degrees divided by 230 and angle of 0 degrees. So that gives me a new current source value of 253 at an angle of 30.68 degrees ampere. Right, compare this with the original I. The original I source was we calculated at 4.348 at an angle of 60 degrees. So the important effect of improving the power factor, so the effect of improving power factors, power factor is number one, lower current value. Now, because of the lower current, then it helps to lower the energy loss. Energy loss in the load. Right, not say the load usually is in the cables, right? Because cables actually carry current, so used to the I square R losses. Right, since I drop, the whole thing will drop as well. Okay, so that is the solution for work example 4.3a. Thanks for watching.